Okay, I think should we study it? And it's my pleasure to introduce our last talk speaker today is the Dr. Vinicius Almeida, and he is the research at the Laboratory of Applied Meteorology, Padua University of Rio de Janeiro in Brazil since 2018. And he has more than 12 years of experience on the geophysical science and software engineering, advanced data analysis, analytical and cloud computing in partnership with Google. And his research area mostly focuses on the development of machine learning models for the many applications and the use of the regional atmospheric model WRF for studying many atmospheric phenomena. Research area, for example, is high impact phenomena for aviations, air pollution, power sector planning, and regional weather forecasts and other advanced data analytic problem in many different sectors. And it's so very welcome to our speaker and Dr. Vinicius Almeida. Please go ahead.
Thank you, Fanqing. Thank you for the introduction. Thank you for the invitation. For the next hour or so, I will talk a little bit about 3 different subjects. They are present here on my title, that are the WRF atmospheric model, that is a regional atmospheric model currently used in many operational weather centers. I will also talk a little bit about that data assimilation, especially how our group has been working with data assimilation to improve aviation nowcasting, that is the short range weather forecast. And also we're going to talk about neural networks. How can we speed up the data assimilation process? As presented by Fanqing, I currently work at the Laboratory for Applied Meteorology. It's a laboratory that is inside the Department of Meteorology at the Federal University of Rio de Janeiro in Brazil, southeastern Brazil. And I will talk, my outline will be this. I will talk a little bit about my background, as already mentioned by Fanqing. I will talk a little bit about my currently laboratory, what our history, our research priorities, and something that we have been working on. A little bit about motivation, both for data simulation and the use of neural networks in atmospheric science. Then I will go to the model itself. I will talk a little bit about the data simulation components of the WRF model. The challenge, how to emulate. Here, we are going to present just simulating the 3D VAR, the variational method that is implemented in WRF model. Then we are going to discuss why should we use a method for emulating a variation method, and some of the future works we have been planning to do. We have been working since the first results we have achieved. So our laboratory today is composed by many researchers, including postdoctoral students, PhD students, master degree students, undergrad, and some associated researchers. Here I present our leader, that current leader, that is Professor Gutenberg Borja de França, that is the head of our laboratory, and also some of the researchers, including myself and many others. So our laboratory is focused on meteorology, but applied to many sectors. And here, just to exemplify, I show some of the areas we have been working on the last 10 years. That includes oil and gas, here with Petrobras, that is an oil company here in Brazil, is a multinational. The National Agency of Petroleum, also, we have already done many researches for them. We have a strong arm for education, not just for our students, but also for partnership with different universities. We have many scientific research, including our partnership with the National Institute for Spatial Research. That is the institute that Haroldo, the Professor Haroldo works on. We have a partnership with them. Also, we have some projects, ongoing projects with the energy sector, including the use of neural networks for charge forecasts, and also for other stuff, and also military. That is the focus here. Military, mainly the Air Force. We have more than 4 years of a project with them, and all my research regarding data simulation started with this partnership. And so the focus here, I will show some results regarding the use of data simulation to improve weather forecasts for aviation purposes. Some of my background, I'm here, this is a biannual meeting that we have at the Department of Airspace Control here in Rio de Janeiro, Brazil, that we have to show our advances to the authorities. And every time we go there, we have an opportunity to exchange some results, some knowledge, to understand how can meteorology be more useful to improve, to avoid fuel consumption, unneeded fuel consumption, to improve the air traffic management and many other objectives. Here, just to illustrate, here it's me. We were at this integrated center for aeronautical meteorology. It has, I think, completed 2 and something more years now. It is an integrated center to coordinate all the meteorology for the Air Force here in Brazil. And we are part of that. We have been helping some researches for them. And we also have a regional group here that is officially registered at the Brazilian National Council for Scientific and Technological Development. Haroldo, Professor Haroldo, is one of the persons that is part of the scientific committee. And it's an important effort to make aviation nowcasting more developed and to improve its results. Here's just some publications, just to give a brief context, just from 2020 to the present. I have highlighted here some publications that myself I have published or contributed, mainly 3 here that I highlight that are publications regarding the use of data simulation to the WRF model to improve weather forecasts for our region here, mainly Rio de Janeiro, São Paulo. This region is very important here in Brazil, and we have been working and producing a lot of research and results regarding this subject. Just again, to give a brief context, here in our area, this is the metropolitan area for Rio de Janeiro. We have a lot of instruments on our city. We have a radar X-band that has been working for something like more than 1-2 years. it gives a three-dimensional field of the wind here in our region. We have solder at the airport, the Santos Dumont Airport, that's the regional airport here in Rio de Janeiro. We have also another solder with the RAS component to measure the profile, the temperature profile at up to 500 meters. So we have a lot of instruments here in our region that we have been using, because these instruments, they are not part of the global telecommunication system, so they are not assimilated in global models. So we have been working with these instruments to make them available for data assimilation in order to improve the weather forecast. Also, more recently, we started working with UNDAR data, that these are aircraft collected data. They include wind information from many levels, when the aircraft is landing or in its departure. It will always collect some information regarding wind and temperature that we can use to assimilate it into the model. If you look, many places in the world already send this information to the global telecommunication system, but unfortunately here in our region, if you take the GTS, the global telecommunication system file for this day, for example, April 6, 2019, you see that this information, this under information is not available. So our models currently do not consider such information for data assimilation. Our group has been working hard to make it available in order to improve weather forecast for our region. Not just for our region, but to generate better conditions that can be used for operational centers in Argentina and other places in the Southern Hemisphere. Now some nowcasting priorities. So our group worked with the Air Force. We have some priorities because we are not working just as a research group. We have a research group with clear objectives. So the data we have available for our studies are meteorological station, radio sounds, radars, numerical models, satellite data, lightning data, UNDAR data, climatology, solar, LIDAR. We have many information available for many locations here in Brazil. And our intention is to use deterministic models, mainly a WRF model, but we work with other models, stochastic models that we can relate to neural networks and other stochastic models, and also hybrid models. That is when we use the output of a deterministic model, like a WRF model, to be the input for a neural network, for example. And these data collection, these models, they are intended to improve the forecast of some phenomena like extreme weather events, visibility, fog that impacts a lot the landing of aircraft. We have also works in wind shear and wind profile. We have been working on how to forecast these short variations of wind profile close to the lanes in airports that can impact the landing. Also sealing to see if some aircraft are not capable of landing without a clear visibility of the airport. And also turbulence. We have some works regarding the clear air turbulence and also turbulence generated by other phenomena. Here's some motivation. Haroldo showed it on the first day of this course. This is taken from the European Center for Medium Range Weather Forecast. This is how they monitor the forecast, the forecast performance. And here we can see, here is our updated version. It's beyond 2020. And here we see both the 3-day weather forecast, the 5-day weather forecast, 7-day and 10-day. And the upper line, solid line, is the weather forecast correlation for the northern hemisphere, and the bottom line is the southern hemisphere. So we see that after 2000, but increasing from the 80s, we have been having this constant increase, and the difference between the performance from the northern and the southern hemisphere is getting smaller. And this is due to the data collection, the data increase, and also the data assimilation process that helps a lot. So this is just to highlight the importance of data assimilation. Here, just as a reminder, of course, I will not get in lots of details because we have already had some amazing talks on the previous days and today also. But here, just to highlight that we have a model, a three-dimensional model that tries to represent many processes that occurs in the atmosphere, and it includes the ocean continent interaction, includes the turbulence, the surface layer, includes the development of deep clouds, include the stratiform clouds. And so we have a lot of process to be represented in our model. And also we have a lot of information being collected constantly on the atmosphere. So if we have this model and we have data assimilation, we can put them together to try to make a better description of the atmosphere that will work as the input of our regional model, because we have received every day a global initial condition that represents the atmosphere in our globe, and we have some particularities that occurs regionally. So we have to take this initial condition, take the data set that we have available in some time window, and try to make them work together to provide a better description of the atmosphere. So this is the basic objective of data assimilation, to provide a better description of the current state of the atmosphere. Here, just as a reminder that we have the model that is on a fixed homogeneous grid, and we have, that is represented here by these white circles here, and also we have some observations that occur irregularly distributed, that is these black squares, and we have to, for each single point, to compute the increment. How can we put this information together to improve the quality of the description of the atmosphere on a determined point, here on grid point? So we have some alternatives that, once again, we have already talked before, so I'm not getting a lot of details, because here my intention is to show some results that we have achieved, not to spend a lot of time in the theory. But here, for the 3D VAR, the 3D variational, we can have a time window here. Imagine that we are going to describe the atmosphere state for analysis time, here represented by 0 hours. If you want to describe the atmosphere, you can define a time window in the 3D VAR approach. And with this time window, we collect all the information, the observed information we have available, and we use some equation like this, a cost function, to try to find the field, the X field that minimized this function. And this function has two different terms. We have an observation term that is composed by the difference between the observed values and the grid values with this observation operator here that converts all the information I have in grid points, in our model grid points, to the observation grid. And we have to take into account the observation errors, the matrix that represents the errors in our observations. And also we have a background term. So we have to see the difference, the increment that we have for each term in our grid points, and also to take into account the background error. So if we have information and we put in this equation, we can have a better description of the atmosphere that will be represented by the X field. In 4D-VAR, it's more sophisticated. We have more slots of time. As explained before, we have a forward model and also an adjunct model that represents the derivatives. Once again, I'm not going to explain it in a lot of details, but the most important that with the 4D-VAR, we can take into account a larger time window and also to evolve the background error covariance. So it's a more sophisticated method, but it's in essence, it has the same principles of 3D-VAR. We have to a slot of time, a slot, and we have to take all the observations that I have available on that slot to make it together to generate a better analysis for our weather forecast. So, but both here in 3D-VAR and 4D-VAR, as I put here on the right, the top right-hand side, I have that both methods, they need a lot of computer power, and that's a problem we have to work. So how can we work with that? So the objective of this line of research I have developed in the late years, I think the last 4 years, is to try to reduce computer power required by data assimilation. In our laboratory, we don't have a supercomputer. Of course, we can have a partnership with an institution that has a supercomputer, but we were trying to find a way to be able to perform data assimilation, but without supercomputers. But is it possible? That was our question. Before I show the answer for that question, I have to show that late on the, I think the last 10 years or so, we have a lot of published articles published regarding the use of neural networks for data assimilation. Here, I highlight some of the publications. Most of them, Professor Haroldo was part of the research. And here are some groups. So we have some publications that uses neural networks for data assimilation using Kalman filter, ensemble Kalman filter, particle filter, some regarding variational methods, space weather, ocean circulation, urban air pollution, hydrology. Here I mentioned the work from Marie, and also medicine. So we have a lot of effort being put to develop neural network models to emulate data simulation or any other process in atmospheric science. So it is very important to understand that a possibility to answer that previous question regarding how to to decrease the computer power needed for data simulation is possibly the use of neural networks. But how to emulate 3D VAR? For instance, here, as I mentioned, I'm not going to show works using 4D VAR or hybrid models. I will focus here today the results in 3D VAR. So how can we emulate 3D VAR in WRF model? So here, just general information about the WRF model is a mesoscale numeric weather prediction system. It is used for both research and operational applications. Once again, I'm not going a lot of details here. I have some information that people interested can go on and to find a little bit about this model if you never heard before. But my objective here is to work with the structure. So WRF model is a complex system that is composed by some data sets. So you should have some data sets available for a WRF model. You have a pre-processing system that is responsible to process both direct observations or some initial and boundary conditions, like, for instance, a GFS from the NSAP data set. We have the model itself that is composed by the data simulation components, the real, that is kind of interpolation, initialization procedure of WRF model, and the dynamical core that is responsible for time iterations for the weather simulation or forecast. And also we have some components here for post-processing, but I'm not getting a lot of details about that. And the data simulation component is pretty much what we have been discussing this week. The data simulation component, it receives a matrix with all the available observations, with R matrix that represents the observation errors. It also receives a background or first guess that usually comes from a previous forecast from a model that can be the same model, what we would call a warm start, if you are using the output of a WRF model to be assimilated in a next cycle. Or it can be a cold start when you take initial condition from, for example, a global model, and use this initial condition to be used for the assimilation process. So with the matrix, the observation matrix and the background matrix, we can perform data simulation to generate the analysis field. That is the field that results from the assimilation process. Also, after the assimilation process, we can update the lateral boundary conditions to make it physically consistent, and then you can use this analysis to be the initial condition for your regional model. So basically, this is how the data simulation components of the WRF model works. And our challenge is how can we replace these WRF-DA components by a neural network? And why is it important? Why would it be interesting to replace this 3D VAR? Let's try to answer such a question. Here, just to explain that our study area is, as I mentioned, the Rio de Janeiro. Here in Rio de Janeiro, we have the international airport, and if we have an area that is called the terminal maneuvering area, that is the area where the airport controls the air traffic. So we work here in this area, So we have two different grids for our modeling system, one with 8 kilometers. We are using initial conditions from the global model with 25 to 27 kilometers. So we have a 1/3 proportion from the initial condition to our coarse grid. And also we have a high resolution grid with 2.6 kilometers approximately. This area is composed by some airports. Here, each name, each symbol here represents a different airport that we have in this region. So our effort is to try to assimilate data collected by these airports. Remember that we are working in partnership with the Air Force, so we are trying to maximize the contribution of each airport, each data collection to the overall result of weather forecast. So we consider all these 5 airports. These 5 airports all have surface information that is composed by wind, humidity, temperature, and other variables. But also here, the international airport, represented by SBGL, is the airport, the international airport, where we have also radio sounds. So we have sounds twice a day, so we can also use the wind and temperature profile to be assimilated into the model. Here's just a summary of the data set we have available. We have surface data for all airports. We have sounding available for the international airports. And also we have the global model that is intended to be used as a background condition, as a first guess to the assimilation process. So first, we develop a sensibility check. So we try to understand how the 3D variational works in WRF model. So we have published 2 different papers. One, this Ciência in Natura on 2020, was part of an event that we attended, organized by Professor Haroldo, regarding micrometeorology advances. And also, we have published in the Brazilian Journal of Meteorology, both regarding the use of use of the 3D variational method and to see the impact of it. Next, after studying the impact of data simulation process in WRF model, we went to the core interest. That is, we try to understand how can we replace the 3D variational method from the WRF model. That's when we published this artificial neural networks for data simulation by WRF model in Rio de Janeiro. And this was the first paper that we have published with our results. But here, as I will explain, we did not use the real data set. First, we have tried to study the assimilation process from a statistical standpoint to understand if I try to assimilate a random noise that here we are calling the white noise perturbation, we expect that this random noise will be filtered by the assimilation process if this random noise is not does not have a bias. So this first study here, we studied the period from 2014 and 2015. We have this kind of flow chart here that shows that first we used the WRF model to generate our target variables. So we take the grid points next to the observation locations. So remember that we used the airport locations, but here we are not using the real data set. Here we took the read points next to each observation location, and we applied a random white noise perturbation to see how these random perturbations would be assimilated by the WRF model. So we used this observation, synthetic observation, and the background collected from the global model into the 3D variational data simulation method of the WRF model, and this generated our reference data set. And on the other hand, the observation and background were used to train two different neural networks that I will explain later how they were developed, the topology, the architecture. But most important, the neural networks, it does not receive only observation. Here we try to develop a concept of the pseudo observations that are not just the observation, but observation and its influence on the surroundings. I will try to explain, but most important that after we had all the target variables and all the training models, we could perform a comparison between the analysis fields and generate evaluation. So let's see how it works. First, our group has, as I mentioned here, we used two different approaches for the neural networks training. We used the WECA software, that is a software developed by the University of Waikato in New Zealand. And also we have used the MPCA, that is the multiple particle collision algorithm that I will talk a bit in the next few slides. But WECA has been used by our group for several research. Here I mentioned two research, one regarding the use of the satellite information for convective weather forecasts in the transition on the route between São Paulo and Rio de Janeiro here in Brazil. And also we have used WECA to work on clear air turbulence forecasts in the route between Santiago in Chile and Mendoza in Argentina. So we have been using WECA, the models available in WECA for quite a while. And also MPCA, that's the multi-particle collision algorithm, has been developed and has been used from 2008. Here the first paper that talks about that is here, loose on 2008, but we have many other works that used this approach. And the basic information about the multi-particle collision algorithm that I think it's interesting to show for you is the cost function, because the multi-particle collision algorithm, it's not just worried about the decreasing the error. Also, the multi-particle collision algorithm is interested in the neural network complexity. So we have two terms here, that a model to be elected as the optimum model, it has to be good, not just in neural network error, but it shouldn't have a lot of complexity. So it makes the multi-particle collision algorithm a good optimizer. It helps you to find the best architecture for your neural networks, and so you can have a better model, but without a lot of complexity. And here I highlight the something that I mentioned before about the pseudo observations. Why I highlight that? Because our raw observations, they are retrieved by single point locations. So if you give to the model, for example, for the neural network model, for the training process, only one information, it will not have a lot of effects on the forecast. It can be considered as a noise. So we try to make the radius of influence of that observation. And here we use it for this research, the Krasman formulation that takes into account a radius of influence of some observation. And this radius of influence, it can be used to propagate the information of such a location for the surroundings. So this is the formulation. Here we have some grid information, and this grid information will be the grid information before this influence calculation, and another term that takes into account a weight that is computed for each observation. So I have a lot of observations available in my study area. So I will compute the weight for each grid point, and I will compute an increment from the observation to the information I have before in that grid point. And also I will divide by the total weight and plus an error to account for possible errors in our observation, in our interpolation and influence. But you can see here that if the distance from the grid point for the observation is too large, it will not be accounted. So that grid point will not be affected by a faraway observation. So this is the basic idea, to create such pseudo observations. So from one single point information that I had in every single point, in every single airport, for every single time step, assimilation time step, now I have an area of influence. Here we used something like 5 grid points to make influence. And so here we have each observation and its area of influence. So when we have an intersection between 2 areas of influence, we compute the average that will propagate for that grid point. And here, an important thing is that observations are mapped to grid points and not otherwise. It's something that I have mentioned in a previous talk, I think in the first or second day, that I have been studying with all the possibilities to, because we have such an increase of information on the last few years, as I mentioned in the graphic of European Center Weather Forecast Performance. So we are imagining that with so much information available, it makes sense to try to evaluate how the model understands the assimilation done on the final grid, not on the, because today on WRF model, and basically what we do is we apply an observation operator that translates the information from grid points to the observation grid. We compute the increment, the innovation, and then we make another interpolation to go back to the original grid. We think that this may cause some problems. I will show an example of a possible problem caused by that, but we are trying to, here, our neural networks, they are done, the assimilation process done on the final grid and not between interpolation process like the classical method. Here just the topologies for our architecture for the MPCA. We have 2 hidden layers for each variable. So we developed 4 different models, 1 for each variable. Some of them, like I said, the MPCA tries to optimize the neural network complexity and error. So maybe I can have a very complex neural networks, but if it does not increase a lot the performance, or decreases the error, it will not be acceptable for MPCA. So here you can see that for air temperature, for instance, we have 2 layers with 11 and 24 neurons in each. But for relative humidity, for instance, we have just 1 layer with 9 neurons. So each model will be adjusted, and also some hyperparameters that are calibrated, are optimized from the MPCA algorithm that is available to you. Also, the WECA topology was fixed for all variables using 2 layers, 25 hidden units, and some other hyperparameters. So just to show the final topology, of course, we tried a lot of combinations, but these were the finals. So some results. Here we have one plot that basically is compares the distribution from the neural networks on the vertical axis and the 3D var, WRF 3D var on the horizontal axis. So as you can see, except for relative humidity, that this for large values of relative humidity, I have a little bit underestimation from the neural network models. They are pre-aligned. This for air temperature and relative humidity, both for the MPCA and WECA models. We also have analyzed the wind components, the zonal winds, and the meridional components of the wind. And also we have a good accordance. We have here for MPCA some problem with the greater values, but overall we have a good accordance between the neural network results and the WRF 3D var results. And that makes a good question. Here, just to show some errors, we see that the errors are very small if we consider that we are trying to emulate the 3D var method, and the errors, they are very small for all variables. But the question is, if the results are similar, why should we replace 3D var? That is the big question. If I cannot improve a lot with neural networks, we should remember that neural networks are intended to emulate a process. So we know that the best, or we expect that the best performance of our neural networks will be related to the target variables. So if the 3D var has some limitations, so the neural networks will have some limitations. So why should we replace? And the answer for this is pretty interesting, because WECA and MPCA were able to run 70 to 100 times faster than 3D var. So imagine that we are working with a partnership with the Air Force. So our final intention is to have a high resolution model working with rapid update cycles with data simulation to prevent, for instance, imagine that we have an extreme event forecasted for our terminal maneuvering area. If I know that at the end of the day, I will have some event, I want to run my model like is done in America. I run my model every hour, collecting information from radar that we have available, sonar, LiDAR. We have all this information. We want to in a fast way, we want to assimilate that in the model, run it for some hours, and to be updating this forecast hour by hour to make the aviation safer. So if you have a tool that makes it available and more, not just to run 70 to 100 times faster, but also it's possible to run it from a personal computer. All these results were done on my personal computer. So I don't need a supercomputer, a big data center. I have a personal computer. I have a server at the Air Force division, and I can run my data simulation with high resolution models without a problem. So this is something to think about. And some highlights here that we had in this first research that were using only white noise perturbations. From up to here, we did not use real data sets. We are just using the synthetic data to emulate the 3D VAR with this controlled data set to try to understand how is the performance of the method. So we had similar analysis produced by 3D VAR and trained neural networks. We have some more standard deviation from neural networks models. I will not get into a lot of details because this can be due to the fact that the MPCA does not like, the correct word will not be like, but MPCA is intended to give some balance between the complexity and the error. So even if I can reduce the error, if it increases a lot the complexity, MPCA will not make the choice of that model. So that's a possibility to explain the greater standard deviation. But these results, this follows previous results, and here I have some reference if you are interested to look for. And also the last highlight is about the performance, the 70 to 100 times faster than the WRF D8 with variation implementation. So after working with synthetic data, we decided to move forward. So if synthetic data works just fine, how it works with real observation? Because synthetic data, they are just some white noise perturbations in information collected from grid points. When you put real observation, we have problems, we have outliers, we have low quality data. So what will happen? So our second phase is including, it's a paper that's under review now in this geoscientific model development, which is very interesting because this journal here, it demands that you publish all your codes, all your algorithms. So we have been working with the review process to make available all the information, all the algorithms we have used in this research. And let's see some results. Here, just a reference. We have this DOI here that points to the repository at Zenodo, that is a demand from the journal, where you can find the data set we have used it in little R format. We have the training models. We have some functions that we have used to create pseudo observations and also to train the models. So I encourage you to go to this URL to check a little bit about this work. And the structure of our flow chart for this second phase of our research was pretty much the same, but now, as you can see, we don't have white noise perturbation between background to generate observations. Now we use real observations and for a greater period. There, we used just the years of 2014 and 2015. Here, we use the whole period between 2015 up to 2019, but we have chosen to leave 2019 for a test data set, and we use it 2015 up to 2018 as a training data set. And now another change is that we did not use the MPCA. We decided to move forward to TensorFlow. That's when we started working with TensorFlow for this process, the data simulation process. And these are the results. Some applications here in our group using TensorFlow. I have some reference here if you are interested and want to check a little bit about that. And some results. Here in the upper left corner, we have the reference data set. I'm not sure if I think some, okay. So upper left corner, we have the control data set. That is something like we have the field that comes from GFS, no assimilation performed using real observations collected from the airports. Here on 3D VAR, we have the result from the data simulation process with the observations collection at each airport. This is just for temperature. The unit here is Kelvin. So you can see that there are some slight changes. There is an increase in temperature here. This part is a urban part that has more buildings and less vegetation. So we have more information here, a greater temperature. And also we have the assimilation process performed by the neural networks. As you can see, we have a greater area of influence because we use pseudo observations for the neural networks and not just the single point observations. So we have a greater area here, but we can see that we have a slightly different behavior, but the main thing is we have the neural networks can take this increase in temperature in the urban area that was expected. If you see the observation information, you see that the expected values was to increase the temperature. And also, interesting here that WECA overestimates a lot the temperature. It makes greater areas of higher temperature. That is something that we were suspicious, but also it can collect some of the behavior of the 3D variational method. Here, the difference between the methods and the control field, as you can see, when you take a look out of the influence area, we have no information because you don't have assimilation outside this area. But the interesting part is that there is a pretty much similar behavior between TensorFlow and 3D VAR. Of course, these areas here in the ocean, they can be a problem because we have computed the influence and not discarding this part in the ocean. But the main thing here is that the behavior is pretty much similar between the 3D VAR and the neural networks. And another example is when we see the profile. Here we have the air temperature profile, average profile in the test dataset. Here we can see the background, that is the GFS, the global forecast model, initial condition, minus the observation, the sounding collected data, observation, and we see the error. So the expected behavior is that the assimilation process will be able to decrease the error between the analysis field and the observation field. So first, if we take a look at the 3D VAR, we see that if I will go back a little bit here, up to 5 kilometers height, we had errors around 3 Kelvin or 2 Kelvin. When you take a look at the 3D VAR, so the profile after the 3D VAR, it reduces a lot the error, and now we have something similar to the observation profile. And the neural networks also can decrease the error between the profile that they generated and the observation. And if you compare the neural networks and the 3D variational method, we see that the errors are very small. So the first thing is we can reproduce the data simulation process. The neural networks are able to run faster, and they can also reproduce the data simulation process. And if you take everything back together, we see that in some parts, here the yellow solid line represents the background minus observation. So this is what we get when you take only the global forecast initial condition. And the other curves are the red, that is the 3D variation curve error. Then I have the WECA error and the TensorFlow. Something interesting here is that we expected that the neural networks would be able to emulate the 3D variational method. But something interesting is that it just not only emulates the 3D variational method, but it also decreases the error. So this is very interesting, and something that is a possible explanation for that. We are still searching, still studying, but something that can explain that is that the 3D variational method, because of the observation operator, the change between grids from the grid point to the observation grid, and then going back with the increments, it might be a source of error. Of course, me and Aroda, we have been working, studying, trying to quantify to see if it really happens if we try to make the assimilation on the grid, the final grid, if it makes it better, makes better results. But this is something to think about, because the neural networks were able to not just to emulate, but to increase the performance of the assimilation process. Just quantifying some errors here. So we have the mean error from the 3D VAR was 0.61 Kelvin, and the TensorFlow was 0.48. So once again, we see that the TensorFlow neural network were able to decrease the error. That is very unexpected, because we are expecting just the emulation, and now we see that we are able, including, to improve the results. And here's some standard deviation just as a reference. And here the most interesting part is the speed. Here we are just showing single cycle and total cycle for the test data set. Each single cycle of 3D variational data simulation took something like 8 seconds, while TensorFlow took like 0.04 seconds. And WECA also just 0.21 seconds. So it's pretty much a speed up in the process, and not just speeding up the process. It makes it possible to run such an assimilation procedure using low-cost computers. So it's something to really continue the research, but also to think about as an alternative for the current method. And some future works we intend to improve, to evaluate the data simulation process using different data sources like solar, LiDAR, and radar. We haven't done it yet. We know that those informations are not currently available in the GTS. So why it is important? If they are not available in the global telecommunication system, they are not considered for the global assimilation process. If they are not considered, and we know that here in Brazil, many centers just use the global initial conditions and run the regional models, they do not perform data simulation. If you can develop a low-cost alternative for such data simulation, is something very interesting that is able to improve a lot the weather forecast here in our region. And also, we want to evaluate the neural networks for other sophisticated methods like 4D VAR and also hybrid that has been talking. It was explained yesterday, if I'm not confused. Because we want the error covariance matrix to evolve with time. And now we are using 3D VAR. The background error is computed from classical methods. It's not evolving in time. And we know that we should implement that because it is able to, we are pretty sure that we can show that neural networks are able to reproduce 4D VAR or hybrid methods with good quality, and that would be incorporated into operational centers. And also, we want to perform this evaluation to compare model grid data simulation to the current observation grid data simulation. We, as I have showed you before, we found some interesting results showing that neural networks, when we perform the data simulation in the final grid, are able to improve, even though it's a slight improve, they can improve the performance of the data simulation process. So if we can evaluate 3D VAR using, we can also use the current implementation of 3D VAR, 4D VAR in WRF model, but try to give information already in model grid points and not in observation grid, and see and compare the results if I let the model perform the simulation on the observation grid. This is something that we want to work on the next research. So it was basically that.
Wow. Yeah, hello. Thank you very much. Wonderful talk. And it's really nice, but I have some questions, but I think they also have some 2 questions from Luke. Maybe you answer these 2 questions first on the chat. Perfect. So first one, does these WRF data simulation systems are actively operational in Air Force model?
Very good question. No, currently they use the WRF model, but they use only the information that comes from the GFS, the global model. But we are working to implement that to the data simulation because we have, as I said, many information coming from under data, that is aircraft data, and we think that they may be very useful for improving.
Okay, there's another question from William, and he said, can you comment whether observation from single source such as need installed somewhere and could still useful to oh, let me think, oh, where it is. Could it still useful for what is now? For analysis, it's still useful. Sorry, I think I'm screen some issues. The last question on the chart, can you see that? Sorry.
Yeah.
Yeah. It's because I have some screen issues. So
okay, no problem.
It keep jumping. So
okay, but I can see William has a question here.
Yes.
Yes, William, I think it can be still useful. Actually, I think it can be pretty useful because if I have the profile, we can create pseudo observations like an area of influence of these observations to a greater area. Of course, every single instrument from the principles, we have to see how much of influence we can compute for them. But of course, it can be used as a simulation. And we also, just some information, we have been talking to a company here in Brazil for a research project in which they have many ships that make some deliveries here in Brazilian coast, and they want to install some lidars aboard these ships. So maybe we can have sometime in the near future a lot of profiles being collected on the ocean for the whole extent of Brazilian coast. That is a very interesting thing to consider in data simulation process.
And another question, can you apply the same approach to other forecast model like the other model, basically bronze, produce development model? Produce develop on a model like bronze. And
yes, of course. Indeed, if I have the results from the assimilation process and the inputs for this assimilation process, so imagine if Brahms uses some set of information as inputs, and I have a very interesting data set of results, target variables from the assimilation process using Brahms, of course, we can replace the assimilation process and to put neural networks to speed up this process, and even improving, as I said, about the observation operator and how can we avoid using that.
Okay, actually, I maybe missed up. Missed your talk some more sense. Can you explain? For your training your neural network, the data simulation neural network, your input, the training data is it's how to generate your training data. So your input is the background plus observations, and then your output will be the analytic results. Is right?
Perfect.
Yes. So how you generate this training data is use the 3D existing 3D systems and generate this data.
Okay. We divide our training as you can see here. We took a greater period from 2015 to 2019, and we divided. We left the 2019 year just for generalization. We did not use it in the training process. So the 2015 up to 2018, we divided into a part, we used cross validation as a training procedure. And we trained on all data sets. And after the training model, when we reached the optimal model, we applied it to 2019. That are the results I showed next.
Yeah, I get it. But I think you have your data, input data for sure. But how about the output data? Output data is come from your 3D data simulation systems, right?
Okay. output.
I mean the input output for your basically for your training data set, you have input, have output, and then you use that as your training your model, and you use part of your data as a training data, and the rest for the validation. So for the training data, you have input and output.
Yes.
It's very clear you have the observation and the background as input. Right?
Okay.
And output, how can you get your output?
We generate our output with the 3D VAR implementation of
Yes.
work model.
Okay. So you use the existing the 3D VAR data simulation systems and to get your output. That's I wonder how can you, that's why I'm really surprised. So you use that, use a 3D VAR data simulation system to generate your data, and you use the data to train your machine learning model, and then you use that training the machine learning model replace the original 3D VAR data simulation model, but your results it's even more accurate than before.
Yes.
Yes.
So that's it's the only this case is only one case, or it's for most of your test case.
The improving. You say the improving.
Yeah. So
right.
I will show. This is an average profile between 1st and 7th February 7th. So this is an average profile. So it's an improvement. And just information, our assimilation process was every 6 hours we had surface information, and every 12 hours we have the sound information. So here we have almost 14 soundings in this case, and the other case we have something like 28 surface observation windows. So this is not just one case, it is the average profile that have been improved.
Oh, really? That really surprised me.
Yeah.
You know, I'm not, you know, I can see, you know, the CPU, the time reduced significantly, and, you know, the speed of the data simulation procedures.
Mm-hmm.
But I don't, okay. It's quite interesting, actually. How can the accuracy also improve as well?
This is very interesting. That's why we started to think about the observation operator, because the only difference is that our training is not performing here. If you take a look here, our training only takes for each grid point the observation background and the target variable. So we are performing the training and the testing already in the final grid. We are not working between grids like the traditional 3D VAR method does to go to observation grid and then goes back to the final grid.
Okay, I get it. So basically, you don't maybe some, you know, avoid some interpolation errors.
Yes, I think so.
Okay, very interesting, actually. Very good work. Nice. And anyone, any else? You know, any other questions?
I think just.
Oh, I think another one is right. I think the result with, okay, that's her with the repeated output with new level data simulation with other. Okay, I get it. Thank you.
So I think that's, I will.
Any
other question?
Do you have any questions? And do you plan, are you planning to apply this method with the ENKF methods? You know, now you replace the neural network with the 3D VARs methods. So in your work, so do you have any work on the data, ENKF combined with machine learning methods?
No, we haven't worked with the hybrid methods or just common filter methods, but we have some literature that Haroldo have worked before that shows the same results, that emulating the common filter, particle filter, we end up with similar results. So the next step for us is to start to use more sophisticated methods like 4D-VAR, because was the first time that we use it in a regional model. This is the first opportunity to operationally, like we are in a partnership with the Air Force, so we have the possibility to make it operational, this kind of assimilation procedure using neural networks. That's, I think, something very new that we haven't done before, and this is something that we have been trying hard to do.
Very good. Thank you very much. And if not any question, oh, another new message. Oh, okay. Result here means performance. Okay, thank you. Yes, and so Haroldo, what do you think? Is any questions? And if not, I think I really, really good, pleasure to have Venezuela here today, and he give very wonderful presentation and the